Cool, so today we have Sophie, Andre, Ellie and Todd. So let's get on to the human molecule. Safety. Okay, before we get into that, first thing that you might notice about us is that we are all wearing our personal protection equipment so that we're able to do these experiments. So we've all got our lab goggles, we've got long pants and closed shoes, and most importantly, lab coats. So I guess, and was it? Oh gosh, anything comes out at you. Okay. Oh gosh.
If anything was to come out at the audience, just tell them not to touch it.
Yep. So if anything comes out of our experiments and lands near you, do not touch it. We also have a few explosions in our shows, so we'll tell you guys when to block your ears. Cool. So we're going to do the human molecule. So there are 3 states of matter. The first one is a solid, so let's all link our hands together. And we are molecules, we are all tightly packed together. We're jiggling it around a little bit. We've got a little bit of energy, so what happens when we become a liquid? We start to form, we start to swim around a little bit, and then if we add some more energy, we become a gas and we start bouncing off walls, we start Yep, let's take away some of the energy, so we're starting to go back to a liquid, moving a little bit slower, a little bit less energy, then take away even more energy, and we are a solid again. So today we're going to go through the 3 states of matter. Our first one will be gases, the next one will be liquids, and finally a solid as we are now. Okay, let's get on to gases.
First up with gases, we have Jess.
Sophie.
Oh, wait. Oh yes, Sophie. I am bad with names.
Okay.
Sorry, I've known you for all of 5 minutes.
So here we got 2 Milo tins that one's going to have vinegar and bicarb, and one's going to have water and dry ice. The vinegar and bicarb is a chemical change, so you can't reverse it at all. And with the dry ice one, it is a physical change, as you can reverse it back into dry ice if it was frozen at a cooler temperature. So with this one, it's going to be the vinegar and bicarb. It will pop, the lid will pop off, and you can't really redo it any more than once. So
Yay! Do it again, do it again.
Is that a mark from it? Or
That was there before you came in.
okay, with the dry ice one, it is. Oh, thank you.
Whoa!
Let's try another one.
That's awesome!
I guess that's enough of that one. Crap. Didn't go up so. Crap.
Okay, let's grab a paper plate.
Behind Andre. Cough, cough, cough.
Oh, do we have a bucket of water?
Yes, yes.
Oh.
Oh crap.
you don't know the explanation of something, look at a presenter or something and they'll talk. Probably.
So normally
A demonstrator.
we are the demonstrator.
Make it sound good.
Yeah.
So, if you get your finger, at any given time, there's always 1 kilo of force being pressed down. Obviously, you can't feel it. And your lungs always got pressure because you're inflating and deflating your lungs and breathing. So, and that's what I'm going to do with this cup, like create some pressure. That's not going to work.
So just hold the cup upright
Oh,
and then
right.
put the plate over
Plate.
the top of it. Yep, like that. And then tip it up. Make sure there's no bubbles. Yep, and then yep.
Now to Jess with the vacuum flask.
Yay!
So the shape we have is determined by the pressure of the air surrounding an object. So like this balloon here. Yep. And what I have here is a bucket. Take the pressure away from it. And what do you think? And I have Sophie here to help me. So what do you think will happen? Yep. Did you guys get a catch of that? Yep. Cool.
It's
So-
inflated.
Okay, now I'm going to get this thing out. And that has 1 pocket of air. What happens if we have something that has 100 pockets of air? Is it 100? Yep. This out.
Lots of fidgeting. Just make sure that it's not wet around that valve area.
Okay. So what do you think could have? Okay. What do you think could have 100 pockets of air?
They're very tasty. Marshmallows!
Yay, marshmallows. You guys want some? Sorry, Ellie.
We don't eat at science experiments, do we, guys?
No. Okay, so. Yep, and what do you think's going to happen this time to the marshmallows?
Ooh,
Yes, Andre?
they're going to expand.
Oh, let's see. Okay, so Sophie, turn it on. Yep, so you have to look really carefully. Can you see what's happening to the marshmallows? Yes, they're expanding.
We're getting mega
Oh
marshmallows!
gosh, they're marshmallows. Okay, thank you, Sophie. And I'll take it away.
Whoa!
Take this thing out again. Yep, and this time we definitely do not eat these marshmallows. Okay, finally we have something that has 1,000 pockets of air. Shaving cream. Oh wait, no, I have to. Okay, what do you think's gonna happen this time? Yay, expanding. Go for it. Oh my gosh, it's expanding. Yep, and off. Look at that.
Ew.
Wait, ew. Yeah.
Ew.
Oh. Okay. Cool. So, now we're going to.
Now we're going to Andre.
Oh.
Who's going to demonstrate some stuff.
Yes,
Oh no,
stuff.
we're doing water.
Yep.
We don't
To
have
make the
water.
bags.
Makes sense. Yeah.
Okay, crap.
Here they are.
So, we are now going to recreate an experiment that happened in the 1500s in a town called Magdeburg. So these things that we have here are called Magdeburg spheres. Okay, so I'm going to have Sophie demonstrate with me. And so I'll say we suck it up. So what's meant to happen is we're going to take the pressure out, and it's going to create this really strong vacuum. And hard to pull, as you can see.
Pull harder.
Oh gosh, yeah. And can we get some volunteers up from the audience who think they might be able to pull this apart? Yay.
Yay.
Yep. So when you guys pull it, make sure you bend your legs a little bit and pull around where your hip is. So in case these come apart, make sure you don't hit yourself in the face. Okay. Can we get another 2 volunteers who think they're stronger than these guys? Yay.
Can I butt in? We have to put our cloaks on them if they come up from the audience.
Yeah.
That's
Yeah.
right.
Okay, so.
Cool. What about now? Okay, cool.
Whoa! How did you do that?
How do you think it happened?
Magic.
So, what we had a little valve here, and it was closed to keep that vacuum inside, but when these guys were pulling it, I tweaked a little bit, I tweaked the valve open a little bit, and it let all the pressure out, so it took away that vacuum. The pressure from the outside then equalized with the inside, and then that's why we were able to pull these spheres apart. Yay.
Yay! Awesome.
Wow, how cool is that, guys? So that was gases, but now we're going to move on to liquids in that part of our show. So liquids have a little bit less energy than gases, but have enough energy to occupy the space of a container. So pretend you're filling up your water bottle. When you turn on the tap, the water's going to fill your water bottle all the way to the top until it's full. That little bit of energy allows all the little water molecules to occupy all the space inside, and that's what we're going to demonstrate here today. So, can anyone in the audience tell me some typical liquids you would find around your house?
Alcohol!
Yes, but today we're not going to drink alcohol because we're responsible scientists of YSA. So instead, we're going to burn alcohol. And as scientists, we're filthy rich. We've got so much money on our hands, and that's why you should look for an occupation in science because you become so rich like Brooke, Ellie, and myself. So, first of all, I want to show you that money can burn.
Are there any fire alarms in here to see?
Yeah.
Okay.
So, wow, look, that burnt really well, guys. So what we're going to do now is we're going to put a bit of propanol on it, or it's also known as isopropanol, which you buy at Woolies. And this stuff burns pretty well, as I'll demonstrate. That goes in there. Boom, boom. Heaps of fire. How cool is that? But now, let's put our money in that fire, in the alcohol. Yeah, it's really well coated there, guys, and as Ellie will light it on fire, whoosh, it didn't burn, and I still got my money. So, what actually happened there, guys? Does anyone have a bit of an idea? Yeah. Well, you're on the right track, mate.
It spontaneously combusted.
Not quite. So what actually happened there was, when we ignited for alcohol, it's actually got a lower ignition point than the paper. And because it's a mixture of alcohol and water, when it burned, when the alcohol burned in excess of 300 degrees centigrade, it evaporated all the water, forming a cloud, almost like a smoke shield, around the paper, and therefore it didn't burn, and we saved our money. That's awesome. So, I know this may sound really bad, but at YSA we try to pride ourselves on how organised we are. But even at the best of times, we can get a bit rowdy, sidetracked. Okay, so we have actually mixed up these 2 liquids. We don't know what they are, and they look identical. And I've heard one of them is poison, and the other one is the cure for cancer. So what can we do to tell the difference between the 2? They look identical. No, we never drink stuff in science because one will kill us and the other one could be really good for us.
Light it on fire!
Not quite, because we don't know the composition, and if it was alcohol like we saw before, we're going to burn the whole place down and it won't be good. So instead, I've got a solution. I'm going to bring out one of my favourite chemicals ever. Well, not chemicals, it's actually a mixture. It's called dry ice. Dry ice, as you know, is frozen carbon dioxide. It's at negative 78.5 degrees centigrade. And the cool thing about this stuff, it's actually a solid, but it doesn't turn to a liquid set. It immediately sublimes to a gas. So when I blow on it, it goes, as you can kind of see. So from a gas solid to a gas without the liquid phase. So I'm going to put this in here and see what happens.
Which one you got? Did you put dishwashing liquid in
No,
one?
I didn't. No, I didn't. Okay, as we can see, there's so much bubbles coming out of here. This must be the cure for cancer. Whilst this other one, it's not changing colour, it's staying the same. Well, I'm sorry guys, we actually played a trick on you. We actually added an indicator to the solution. We added an indicator to the solution. What an indicator basically does is, an indicator can tell us whether the solution is acidic or basic. So we have this spectrum, it's called the pH spectrum, and we can measure how acidic or basic something is. So we all know we've got acids like lemon juice and hydrochloric acid that are very acidic and can corrode stuff really easily. Whilst down on the other end of the spectrum, we've got products like bleach and
Dishwashing detergent
that are still corrosive, but they're opposite on the side of things. And whilst in the centre, we've got water, which is neutral altogether, which is neither acidic nor basic. So in this experiment, we actually added phenolphthalein indicator. Bromophenol blue, which is an indicator. And basically it informs us that
Mine's a bit yellow, but you know.
if it's...
It is yellow.
It is yellow. So we've seen its colour change. So when it's gone yellow, it indicates us, since we've added the dry ice, it's turning more, it's gone from an acid, from a base, all the way to neutralisation at around about a pH of 7. So now we've also got heaps of other cool experiments with indicators, as Todd will present.
So you've seen bromophenol blue, which changes colour in the event that it's put in an acid. But it doesn't really show whether something's basic or acidic. For that we have the universal indicator. Who has a pool or a fish tank?
Me!
Yeah, your parents have probably used the universal indicator to see what the pH of the water is so that it doesn't kill your fish or it doesn't burn your eyes when you swim in the pool. I've got a little bit of universal indicator in this cylinder here, and I'm going to chuck a little bit of dry ice in there. Now this dry ice, when it reacts with the water, it forms carbonic acid. Call out the colours as you see that. Freaking hell, that went fast.
Yellow. Yellow.
Yellow.
Yellow.
Yellow.
More yellow.
Well, as you can see, it's starting to go orange now.
Yellow.
Hello.
Yellow.
Hello to you too.
I'm going to help it along a little with a little bit of this hydrochloric acid, which is a very strong acid. And as you can see, it very quickly turns red, which is the other end of the spectrum. So we started from a basic substance like dishwashing detergent, which shows up purple on this universal indicator. And we've gone all the way to a very acidic substance, hydrochloric acid, which shows up as red on this indicator. Now, it was my birthday next weekend.
Also.
And I decided that I wanted a little bit of cordial, but we only had water. So, you know, at my birthday, I like to pull off a little bit of science. So, I decided to turn that water into cordial.
Whoa!
God. It's so pink.
That looks...
But then my mother came out and said, we're all too hyper, so we need to turn half of that cordial back into water. As you
Whoa!
can
It's
see.
water again.
It's water again. But you wouldn't want to drink this. This has phenolphthalein in it. Phenolphthalein is another one of those indicators that only shows one side of the pH spectrum. when it's in a basic solution, phenolphthalein will turn it pink. In this beaker, we had a little bit of sodium hydroxide, which is very basic, which turned it pink. And in this one, we had a little bit of hydrochloric acid, which neutralized the base and turned it back clear. Phenolphthalein used to be used as a laxative. Now we have Ellie to present, Ellie and Sophie, to present the solids section of our show.
Thanks, Todd.
Here.
So, we talked about both gases and liquids now. So, the third one that we want to talk about is solids. So, who can name some solids for me?
Chocolate.
Yeah,
Bricks.
technically. Bricks, yeah.
Iron.
Iron, yeah. Anything else? What's in front of me here?
Glass.
What's this?
Styrofoam.
Styrofoam, polystyrene. Yeah. So you can have two different types of solids. You see this hammer here? Do you think I could break this with my bare hands?
No.
I don't think so. That's a pretty hard solid.
Overwhelming.
Whereas this polystyrene I have here, I can snap with my 2 fingers. 4 fingers. And so what I'm going to show you today is how bonds can be broken down. So I've got some acetone here, and acetone it may look like things are melting, but they're not. So if I put some into this polystyrene right here, look at that. Can you see that melting? It's not actually melting. What's actually happening is the bonds in this polystyrene are actually getting broken down by the acetone. You may find it in some nail polish removers and everything. So I can actually pick this up and play with it. You see that? So it's actually pretty fun to play with. But what's actually happened is that if I could grab Sophie's help here, I'm just going to take these gloves off. As you saw in our YSA molecule before, we had bonds that were like this. And they were pretty brittle. If you had something here, they could snap pretty easily. That's what I could do with that polystyrene there. And what's actually the acetone has done is it's actually created a bond, so we're actually quite a liquid now, which is what it actually looked like in my hands. It looked like slime almost, didn't it? So that's a pretty cool thing that you can do with acetone and polystyrene. Now what I'm going to do is, we looked at some pretty cold stuff before. We had some dry ice. I'm going to look at something even colder, and that's liquid nitrogen. Do you guys like liquid nitrogen? You've seen it before? You guys are my audience.
Yeah.
So, I'm going to get some liquid nitrogen out. You guys want to see something really cool? Whoa. Yeah, it's pretty cool, hey? So, we have some different types of plastics here, guys. I have a little rubber ducky or rubber whale. I have a balloon. And I also have some flowers. What's going to happen is I'm going to put liquid nitrogen on these things. What do you think will happen to this balloon when I pour liquid nitrogen over it?
It's going to spontaneously combust.
Maybe. Anyone else?
It's going to implode.
Okay. I want you guys to be very, very quiet and listen to this. So you can hear the balloon when you first hear that rubber. Now listen to it as I pour some liquid nitrogen on it. actually also cooled down, so they weren't moving as fast, and that means they weren't actually creating pressure on the outside of the balloon, which was actually inflating it. So when I cooled it down, it crinkled, and when I heated it back up, it came back to its normal state. So now we've done that balloon. Who's played in the bath with some little rubber toys before? Yeah, you want to see what happens when these go in some liquid nitrogen? Let's have a look. He's all gone. What happened? So because there was a different type of plastic, he actually broke when he got cooled down. Do you guys want to... So normally you have Barbie. So I normally do a Barbie. Anyway, we did a Barbie. Yay! Smash. Oh no, Barbie's gone. And now go into different clothing, hair, all that kind of stuff. So what the difference is between those plastics and these flowers. These flowers are actually organic, so they have cells. And when cells go cold, they freeze, and water expands when it freezes. So if I freeze these, will they go back to a normal state? No? Let's have a look. Okay, these flowers are pretty cold now. Let's see what happens. Oh no, the poor flowers!
Whoa.
So you can see that they crumpled quite like they did with the other plastics. But what you could probably see is that with these plastics, that's still cold. You can actually pick it back up, and when it's warmed back up, it will go back to its malleable state. So you can still bend it, and it will still move like it did when it wasn't actually broken. But with these flowers, because all these cells have now burst because of the expanding water in them, they'll just wilter and die, unfortunately. So that's the end of our solid, liquids and gas, but we have a really cool last explosion for you guys. You want to hear a big explosion?
Yes!
Okay, let's do that. And we proceed to do